now it's the turn of Alex Soto, and he's going to talk about dynamical Majorana neutrino masses and actions. So please, Alex, go ahead. I will let you know after 10 minutes.
Thanks. First of all, thanks to the organization to give me the opportunity to give this talk in this workshop. Again, this topic is different from the previous editions. In that cases, we are talking about very special relativity, but now I am going to talk about dynamical Majorana neutrino masses. And the talk plan is the following. First of all, I will introduce the model. A very important introduction was done by Nick in the previous talk, so I won't go deep into the model, but the main question that I would like to answer in this time is if we can get the dynamical mass for the axion and fermion. And for this purpose, we will proceed using the Schwinger-Dyson analysis, considering a YUKAWA interaction. In that case, we will use Hermitian and non-Hermitian, which is connected with ET formalism. This is a work that we published in nuclear physics together with Jan Alexandre and Nick, who presented before. And after we discuss the Schwinger-Dyson analysis in this case, we will add anomaly terms and the background, which is connected with the leptogenesis that he mentioned before. This is a work that appeared recently too in nuclear physics. So finally, I will summarize and we give some comments. Well, the model is the following. As you can see, the main ingredients of this model is the presence of this axion that we can see. Obviously, this axion comes from a string model, so we can consider a lot of species. Here we will consider only one. It could be a moduli or the Karl-Raman field that generate this axion. And the fermion, in this case, this fermion is a Majorana fermion. It is the stereo neutrino. In that case, that we have here. Obviously, the axion has not potential, as Nick mentioned it before, but some non-perturbative effects could, may appear. The apparition of this term, this YUKAWA interaction, that we will see in the next slide. And we have here this coefficient. We can replace by only one term, but I give this term in this way because you can see the gamma appears here and here, and the gamma is restricted to be small than 1 in order to be real and to get an Hermitian term. The Hermitian term is usually in quantum mechanics in order to get an real spectrum. But if you do analytic continuation of these parameters gamma and lambda, we can avoid this restriction on gamma. And the consequence of this is we have now in this term, for example, non-Hermitian term. So the important connection that we can make with these elements, the work of Fender and Betcher, because they show that non-Hermitian terms, but respecting PT symmetry, they could have a real spectrum. So basically, we are dealing with non-Hermitian interaction. This is the novelty of this work. We will consider that element, consider this YUKAWA interaction and Hermitian and non-Hermitian. And what is the consequence of the non-Hermitian terms in this case? So this term, basically, since a Majorana fermion, we can write this in this way. So basically, this is a YUKAWA interaction. And this term related with the anomalies, we can write in this way, which is connected with the derivative of the axion and the chiral current. So in addition, not only we will deal with these terms, we will add the axial background as is in this paper, the connection with leptogenesis cases, and we will consider the B as a constant. This B mu is the background. So in this case, we will consider this kind of term. We will keep it as general as possible, but keeping in mind that the B is a constant. So basically, the Lagrangian is given by this the subject, the axion, and the fermion. An important comment that I will give here is we will consider as a prototype model Dirac fermions. It doesn't change the conclusions with the respected Majorana case. It only changes 1/2 that appears in the middle, but qualitatively it doesn't change the consideration of Dirac masses. So, well, we have the kinetical parts, the anomaly term, the background term, the YUKAWA term, but we add this term, which is for Fermi interaction, an attractive for Fermi interaction that we put here, and later it will be important in our conclusion. So the important question, and this is the aim of the talk, is if we can get dynamical mass for axion and Fermi. So for this case, we proceed first using Hermitian YUKAWA interactions. We turn off the background and the anomaly term. Here we have obviously the kinetical part of the axion and the pseudoscalar field and the fermion, the YUKAWA term, and the four fermion interaction that will be important later. After linearization, as usual in this kind of terms, we get this, and we will proceed using the Schwinger-Dyson equations. So if we want dynamical mass, the solution of the Schwinger-Dyson equation should be consistent. So we need to consider the mass for the pseudoscalar field and the mass for the fermion field. And using that Schwinger-Dyson equations and under the consideration of rainbow approximation, which is justified in our calculation, which means that we neglect the corrections to the vertices, we use the cutoff regularization. It introduces this cutoff, which is the highest scale in that case. We will consider it a Planck scale, so it's okay. And this consideration, the masses of the fermion and the pseudoscalar field are the same. Basically, this is in order to get an analytical solution, we get the full Schwinger-Dyson equations, but the solutions are very complex in order to deal analytically. And in this case, obviously, in order to get an analytic result, we will restrict into this case. So if you see here in the second equation, this is the is coming from the scalar case. You can see here this element is positive because this element is the highest scale, and M obviously is this result is positive. So with this minus sign, we have an inconsistency here. The mass square is a minus, is a negative quantity. So it means there is an inconsistency. It means that there is no dynamical mass for the scalar particle. So the only way to bypass this consideration is to add a bare mass. This is the point here. If you have a bare mass to the scalar field, we get a consistent equation in that case. After the computation, the solution should be consistent. We have to check this is bigger than this term after our computation. So we have this, and we have this equation for the fermionic part. If you don't consider this term, which comes from the four fermion interaction, both equations are not consistent. So we need to introduce this term in order to get a dynamical mass for fermion and the scalar field. Our results after solution of this equation of the Schwinger-Dyson equations, we get these results. The F4, which is the coupling, basically is of this order, is proportional to the cutoff, and the masses are given by this element. We get a proportional to lambda square, and this capital lambda, and this small lambda square. So this is the result is smaller than this, the highest scale. It is consistent. The result we found M0. If we subtract it, we get M. It's positive should be. So there is difference when we consider non-Hermitian YUKAWA. If the YUKAWA interaction is non-Hermitian, the situation is different. As you can see here in the second equation, this equation comes from the scalar field is exactly the same as the previous case, but without this minus sign. So this element is positive as before, but in this case it's positive. So here the important lesson in non-Hermitian YUKAWA interactions, we don't need to introduce any bare mass in order to get dynamical mass for the scalar field. In YUKAWA interaction where it's Hermitian, we need to introduce this bare mass in the beginning, but here when we consider non-Hermitian case, we don't need because it's favorable. But the case in the fermion is completely different because we have here this minus sign. If we don't introduce the form fermion interaction, it is impossible to get dynamical mass for the fermion. This is consistent with the energetic arguments that were given in this paper. So the explicit calculation with Schwinger Dyson equation reveals that it is impossible to get a dynamical mass for the fermion unless we introduce this for fermion interaction. If we do that, we get these results, which are consistent. We get a dynamical mass for fermion and the scalar field. Now,
4 minutes, Alex.
Okay, thanks. So we introduce the anomaly term, which is Hermitian, and Hermitian YUKAWA. We will keep Hermitian because we want to introduce some instabilities in the system. In that case, if we proceed as before using the exactly the same procedure, we get these equations, Schwinger Dyson. If we solve it, we get these situations. As you can see here, we have gamma and G. G is the term related with the for fermion interaction, and gamma is the coupling constant with the anomaly term. As you can see here, in all the cases, they have the same sign. So here, in the Hermitian case, the term, the for fermion interaction and the anomaly term plays a similar role. They assist the dynamical mass generation in this case. But if we consider non-Hermitian anomaly, the situation is completely different because if we can see here, the sign is the opposite. We have here a minus sign. So in this case, when we consider anomaly, a non-Hermitian anomaly term, it resists the dynamical mass generation. The only way to get dynamical mass generation is the consideration of G squared is higher than gamma squared in order to get this real. So if we add Hermitian backgrounds, the important lesson here is if we consider M0, which is the bare mass equal to 0, we plot here this equation. The left-hand side is 1, this is the purple line, and the right-hand side is this, and it never intersects. So there is no solution unless we introduce bare mass. So the important lesson, after all, is in the Hermitian case, we always need to introduce a bare mass in the beginning in order to get a dynamical mass generation. And the fermion equation is this. This is the plot of the right-hand side. The left-hand side is this constant line. And there is dynamical mass generation when the background is small. If we increase the background values, we don't get, because we get this curve, for example, it doesn't intersect with this curve, so there is no dynamical mass solution in that case. The different case is when we consider non-Hermitian YUKAWA, as we saw before. It's favored the dynamical mass generation of the scalar field. It always intersects. And the fermion equations, basically, we have this, it's very complex, but the plot is this, and they intersect in this point, so it means there is dynamical mass generation when we have this situation. The same occurs when we have no Hermitian background, and here the difference with the previous case when the background is Hermitian is that always we have dynamical mass generation, but the larger the background, the bigger the mass. It's the opposite case from the Hermitian case. But again, we need to introduce the bare mass in order to have the dynamical mass for the scalar in order to these lines intersect. This is the values per time. I won't stop in that case. And finally, the non-Hermitian background and non-Hermitian YUKAWA as non-Hermitian YUKAWA, we have this situation in the scalar case, and in the fermion and the scalar is this line, we get the dynamical mass generation. So basically, to summarize and to make some remarks, we have learned about the Hermitian YUKAWA coupling. The scalar mass requires the existence of bare mass in order to have dynamical mass generation, and the fermion is required in order to have consistent solutions in the Schwinger-Dyson equation. Non-Hermitian YUKAWA coupling, the scalar mass, we don't need to introduce this bare mass, and for fermion interaction is required because the fermion Schwinger-Dyson equation doesn't favor the fermion mass, but we need to introduce this for fermion in order to get the dynamical mass. The Hermitian anomaly assists the dynamical mass generation. It plays the similar role of the for fermion interaction, but in the non-Hermitian case, it resists this object. It plays the opposite role. And we here have the non-Hermitian background. Larger the background, larger the mass, and the opposite case in the Hermitian background, when we need to have a small background in order to get a dynamical mass. We here have reviewed some important aspects of the model, and we have introduced non-Hermitian potential and the effects on the dynamical mass generation. This is a very grown topic, so we would like to explore more details in these cases, because in this case, as you can see, it favors some scalar mass, and it is important to review more things that we don't knew before. So thanks for your attention.
Thank you very much, Alex. Let's thank Alex. So we have like 3 minutes for question. The first question was from Lucas Maldone. Please, Luca, go ahead.
Okay, thank you. Can you hear me?
Yes.
Yeah, okay, good. Now, just a curiosity. But if you want now to complicate a little bit more, it's not simple, but and we want to introduce also mixing generation. Since you start, for example, with 2 families of fermions, and so you need more complicated condensate structure, which mixes both generation. How do you think that this could affect also the scalar part, or are independent, or?
Oh, we only consider one species, because obviously the Schwinger-Dyson equations are very complex. In this case, obviously, we proceed in this case using this approximation in order to get an analytical result. If we add more species of axions, because the model allows the existence of more axions, this is only one. We can mix both axions, and we can add more fermions, obviously, but they complicate a lot of the computation of this case. So the only way to proceed is numerically, but we would like to get an analytic flavor in order to get because the main aim of this work is to answer the question if we can get dynamical mass considering the YUKAWA interaction. This is the only point. Obviously, we can use more species of axion and fermion, but it's very complicated to do analytically. This is the point.
Yeah, I can understand, but do you think this will lead, for example, to you have some maybe now to generation of axions, and so mixing of fermion will induce something like mixing of axions, or?
Oh, sorry, again, please.
Do you think that mixing a level of fermions, if you generate mixing a level of fermions, this could also imply mixing a level of axions, or they're independent?
Well, this mixing comes from non-perturbative effects of the string model. So we are only considering this term. I don't think if it is possible to connect it up.
Okay.